And here are our responses. Okay, these are our options. Okay, some of them are the correct answers. All right, anyway, so let's do this. Now, I want to mention one other thing before I dive into this question, okay? So when you read this question, I know that we haven't talked about electrical conductivity of solutions. But the thing is, I don't have to, okay? The reason is you are told in the question, for a solution to conduct electricity, we need free ions. Only thing that you need to do is determine which one of these compounds will generate free ions when it dissolves in water. Okay, that's the only consideration that you need to have here, right? And then how do we do that? So if you have an ionic compound with a charged product, and this is what you need to recall here. First of all, you need to have an ionic compound, okay? And the charged product of the ionic compound, that is charge of the positive ion times the charge of the negative ion, the absolute value of that, if this value is greater than or equals to 4, then this is going to be insoluble. And this is insoluble. Okay. So this is the mantra. In other words, if the charged product, let me write it out for you, even though it is already implied here, okay, is less than 4, then it's going to be soluble. So this is the only requirement that you need to look for. Okay. Soluble. All right. Now, with that in mind, let's look at CH4. I need my thing. Okay. So let's look at CH4. Is CH4 an ionic compound or a covalent compound? Everybody, is it ionic or covalent? It's a covalent compound. So it doesn't have ions to begin with. So if you put that in a solution or a water sample, it will not generate ions. Okay. Therefore, CH4 will not produce a solution that conducts electricity. And lithium nitride, okay, lithium is +1 and nitrogen is always -3. Therefore, the charged product, okay, the cation charge times the anion charge, will take the absolute value of that is 3. Therefore, this is soluble. Therefore, this will conduct electricity. Aluminum nitride, aluminum is +3, nitrogen is -3. How do we know this? Aluminum is in group 3. It's going to remove 3 electrons to become like a noble gas. Therefore, it's going to form +3. Nitrogen is in group 5. It's going to gain 3 electrons to become like a noble gas. Therefore, it's going to form -3. Therefore, the charged product is 9. Okay, this will not be soluble in water. Therefore, this is insoluble, right? If it is insoluble, it will not conduct electricity. Magnesium nitride, there's a typo here. This should be 3 and this should be 2. Okay, magnesium is +2 and nitrogen is always -3. The charged product is 6, therefore insoluble. Therefore, this will not conduct electricity. So these guys are out. And CH3NH2, is it covalent or ionic? Everybody, CH3NH2, covalent or ionic? It's a covalent compound. It doesn't have ions to begin with. Therefore, it will not generate ions or a solution that conducts electricity. Okay, I believe that there are more below. Let me clear my doodling. Okay, and aluminum nitrate. So aluminum is +3, and nitrate we know is -1. Therefore, the charged product is 3. Therefore, soluble. Therefore, this will conduct electricity together with this guy over here. Okay, and calcium nitrate. Calcium is +2. Nitrate. This whole thing is a polyatomic ion with charge of -1. Therefore, the charged product is 2. Therefore, this will be soluble. Therefore, this will conduct electricity as well. Therefore, the correct answers are options B, F, and G. Now, in the second question, you are told that you have 1 gram of each reactant, and then you are asked to determine the mass of lithium chloride, one of the products you are going to get. Okay, so what I'm going to do is this. So you are given 1 gram of this and 1 gram of this, and then you are asked to find the mass of this. Okay, mass of lithium chloride. So first of all, determine what they are asking. Okay, so what is given and what they are asking. Okay, to do this, in the thinking method, you first need to determine the limiting reactant. Okay, But there's another way to do it without determining the limiting reactant. You can try both calculations. One, assuming the limiting reactant is lithium sulfate, this guy over here. And the second calculation, assuming that our limiting reactant is aluminum chloride. So let's try lithium sulfate. Okay. If lithium sulfate was our limiting reactant, okay, and how much lithium chloride will we get? So this is how we do it. We have 1 gram of lithium sulfate. Okay. But what we want is not the grams of lithium sulfate. We need the grams of lithium chloride. We need to go from grams of lithium sulfate to grams of lithium chloride. How do we do this? First, we need to cancel this out, grams of lithium sulfate. How do I do that? If I divide this by the molar mass of lithium sulfate, which is, lithium is, I think, around 7. You have 2 of them. And then sulfur is 32. Is that right? Please, someone should help me. 32. And oxygen is 4 times 16. Is that right? Sulfur relative atomic mass is 32. Is that correct? Okay, thank you. Okay. So if you add these up, we have 14 plus 32 plus, I think this is 32, 64. 64 plus 32 is 96. 96 plus 14 is, I think, 110. I think. Please correct me if I'm wrong. Okay, I'm doing this in my head. 110 grams of lithium 2 sulfate in 1 mole of lithium sulfate. Okay. Why did I do this? So that I can cancel out the grams of lithium sulfate. Now I'm in the mole space, right? Now, once I'm in the mole space, I need to do moles of lithium sulfate to moles of lithium chloride. How do I do this? Using the balanced chemical reaction. I see that lithium sulfate in the balanced chemical equation, I have the coefficient 3 here. So I'm going to write 3 mole of lithium sulfate here. Why did I write 3? Because there's 3 in front of lithium sulfate in the balanced chemical reaction. And then in the numerator, I'm going to write 6 lithium chloride. 6 mole lithium chloride. Why did I write lithium sulfate in the denominator? So that I can cancel it out with the moles of lithium sulfate in the numerator over here. Okay. So I am in moles of lithium chloride now at this point. But I don't need moles of lithium chloride. I need the mass of lithium chloride, right? So I need to cancel out moles of lithium chloride as well. So I'm going to divide this by 1 mole of lithium chloride. And then I know 1 mole of lithium chloride has the mass of 35.5 plus 7, 42.5. Let's call it 42.5. 42.5 grams of lithium chloride. Can somebody verify it? Is it correct? Is molar mass? Okay, perfect. Thank you. And then we see that I am now canceling out the moles of lithium chloride with moles of lithium chloride. I'm going to get my answer in grams of lithium chloride. Can you plug these numbers into a calculator and chug it? And let me know the answer. Plug and chug. What did you get? 0.77. Okay. So I heard that you are going to get 0.77. Is that right? All right. 77 grams for this. All right. Now we need to do this again. So we don't have to think too much. Now this is assuming lithium sulfate as my limiting reactant. So let's say that aluminum chloride was your limiting reactant. So let's do the same calculation with aluminum chloride now. All right. So we have 1 gram of aluminum chloride given. We always start with what is given, but we don't need the grams of aluminum chloride. So I'm going to divide this by the molar mass of aluminum chloride. So aluminum is 20. So what's the molar mass of aluminum chloride? Can someone tell me? We have anybody? 113.5? 130.5. Okay. So please verify it. We have 130.5 grams of aluminum chloride in 1 mole of aluminum chloride. Can somebody else verify it? Is it correct? 133.5? Okay, 133.5. How do we get this? Aluminum is 27, I think. And then chlorine is 35.5. You have 3 of them. So you just add this up. Okay. So 71 plus 35.5, 106.5, 106.5 plus 27 is 133.5. Makes sense. Yeah, do this with your calculator. You don't have to do it to your head, okay? All right, anyway, so that's that. But why did I do this? So that I can cancel out the grams of aluminum chloride. Now I'm in moles of aluminum chloride. Now I want to convert this to moles of lithium chloride. So from the balanced chemical reaction, I have 2 in front of aluminum. Therefore, I'm going to write 2 mole aluminum chloride here, aluminium chloride. And then in the numerator, I'm going to write 6 moles of lithium chloride. Why did I do that? So that I can cancel out the moles of aluminum chloride. And now I want to convert this to grams of lithium chloride. Why no? 1 mole of lithium chloride has a mass of 42.5 grams of lithium chloride. Okay, so therefore, the moles of lithium chloride cancel out. You're going to get the answer in grams of lithium chloride. What do you get? Anybody? Yes, please. 0.96. 0.96 grams. Okay, now we're done. All right. Now here's what we do. We pick the smaller number. Smaller number out of 0.77 and 0.96 is 0.77. So that's our answer. Okay. And therefore, we also know our limiting reactant is lithium sulfate, not aluminum chloride. The reactant that gives the least amount of the product is our limiting reactant. That you need to know is at equilibrium, okay, you need to know that rate of the forward reaction, I'm going to call it rate sub F, meaning reactants becoming products, rate of reactants becoming products is equal to the rate of the reverse reaction, meaning the rate of products becoming reactants. Okay, this is what is true at the equilibrium. I should have wrote this in blood. I'm sorry, in red pen. But anyway, so this is really important. This is what equilibrium means. Okay, so it doesn't mean that at equilibrium, the reaction stops. Reaction does not stop at the equilibrium. Okay, what happens is the rate of production of products and rate of production of reactants is going to be the same. It seems like the concentrations at the equilibrium are not changing. Okay, therefore, let me write that too. Therefore, at equilibrium, it seems like the concentrations of reactants and products are not changing. Products are not changing. But this is just an illusion, okay? It is changing, but it's changing at the same rate. That's why it seems like it, okay? If you are more like, graphically oriented, I mean, I'm going to draw this as well, okay? Let's say that we have concentrations on the y-axis, and this is time on the x-axis, okay? What is going to happen is, at the beginning, we have a lot of reactants. We have a high concentration of reactants. Okay? With time, the reactant concentration decreases until it reaches a constant value. It seems like it's constant after some time. Okay? This is my reactant concentration. On the other hand, when it comes to products, product concentration increases with time until it reaches a certain point. Okay, after that certain point, it seems like the product concentration is not changing. Okay, and that point where the concentration starts to not change, okay, this is the point where the system achieves the equilibrium. Okay, this is the time point. Time at which the system reaches, or let's call it reaction. The reaction reaches the equilibrium. Okay, what happens after that? After that, it seems like nothing is happening, but in actuality, okay, products are becoming reactants and reactants are becoming products at the same rate. Therefore, it seems like nothing is happening. Okay, and this is what we call a dynamic equilibrium. Yeah, it's dynamic, meaning it's still moving, but it seems like it is constant. Okay, so equilibrium is not the end of the reaction. Okay, so at equilibrium, the rates of the forward and the reverse are equal. Therefore, it seems like the reactant and product concentrations are constant. Okay, now I'm going to talk about the question and then I'll take your questions. Okay, so on top hat, let me show you. If you take system 1, all right, at T0, we have all reactants because the orange ovals are the products. Okay, at T1, it's 3. At T2, it is 5. And at T3 is more than that, meaning the concentrations of products is changing. Okay, therefore, we don't see that the system 1 has reached equilibrium at this point. You know what? I want to stop collecting answers for the moment. Okay, and then when it comes to system 2, okay, the concentration of the products products and reactants change up until T2. After T2, you see that the concentrations of the number of products is the same. Okay, after T2, it is not changing. So here we have achieved the equilibrium at this point. This is where we have achieved the equilibrium point. It's not equilibrium point. Beyond this point, we have achieved the equilibrium. Okay, so this T2 and time T3. Okay, we know that system is in equilibrium, and in system 3, we see that the concentrations are still changing even at T3. We don't have enough information. By the time, at time T3, the system has not achieved equilibrium as far as we are concerned because we do not know what is going to happen at T4, right? It is not available here. Therefore, system 3 has not achieved equilibrium. Neither system 1, only system 2 has achieved the equilibrium. How do we know it? It seems like the concentrations of reactants and products are not changing. Okay, for example, the product concentration, which is the orange ovals, are not changing after time T2 here. Therefore, it has achieved equilibrium. All right, I'll give you 30 seconds to think about this, and then I'll take any questions you might have. Jocelyn. No, it's asking what time point?
And like T2.
We should equilibrium at T2 time.
No, so it only reaches equilibrium at one point in time. And then like it stays in equilibrium. Yeah.
Yeah. All right. Now, what's the answer for this question? The answer is, okay, let me read the question back to you. Which, if any, of the systems shown has reached equilibrium? Only system 2. And at what time point? Okay, at T2 time point, the system 2 has reached equilibrium. Okay, therefore the answer is system 2 and T2. Okay, we know that at T3 the system is at equilibrium too, but it achieved the equilibrium at T2. So they're asking for that. At what time point the system has reached equilibrium? It's going to be T2. And T2, T3, T4, T5 to infinity should be at equilibrium still. All right. What other questions, concerns, comments do we have about this? Harshini, are we doing okay there? All right. So with that, I'm going to clear my doodling and I'll maybe reopen the question. 2 and 1. All right. And here are our responses. Most of us selected option C, which is the correct answer as well. Okay. Now, what questions, concerns, comments do we have about this? The second most popular answer is option D. Why isn't D correct? Any? Do you have the microphone, Famida? And can you shout for the moment? Thank you. If not for water, thank you, Annie. Okay. If we did not have water in our question, okay, then if somebody asks you the submicroscopic structure of calcium chloride, this would have been a correct answer. But in water, we know that we predict this to be soluble, right? Because calcium is +2, chlorine is -1, the charged product is 2, which is less than 4. Charged product is, by the way, the absolute value of it. Cation charge times the anion charge, absolute value is 2. Okay, this is less than 4. Therefore, we predict this to be soluble in water. Okay, when ionic compounds become soluble in water, dissolves in water, they separate into individual ions, meaning we are not going to get D, we are going to get C. All the ions are separated now. Okay, that's why option C is the correct answer. Okay, and these ions will be surrounded by water molecules. Okay, but I mean, we are not showing that for the moment. All right. Do we have any questions, concerns, comments? I just, another question came to my mind. Do we have any questions, concerns, comments? All right, let's do this. On your whiteboard, show me how the water molecules arrange around, let's say, the chloride ions. Go ahead on your whiteboard. How do you expect the water molecules to arrange around the chloride ions? All right. So I have chloride ions, which is going to have a minus charge. All right. And this minus charge will be surrounded by water molecules, but tails of the dipole moment of the water molecule will be facing the anion. Okay. Tails will be facing the anion. And if you want to draw the water molecules over that, you can do that as well. So if you draw the water molecules, should be something like this. Right? So they are going to be separated and it's going to look like that. And the cations would be the other way around, right? So for the cations, the heads of the dipole moment, which has a partial negative charge, will be attracted to the positive charge of the cation. Like that. All right. What questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? All right. So with that, let's do another one. All right, I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses. Yeah, most of us selected option B without any doubt. Okay, increase in temperature will make the molecules move faster. Therefore, there'll be more collisions. More collisions lead to faster reactions. So we know higher reaction rates. That's number one. Okay, and then the other thing is, okay, now keep this in mind. There's only one way to decrease the activation energy. What is that? How can we decrease the activation energy? Yeah, using a catalyst. That's the only way. Increasing temperature does not, okay, affect or touch the activation energy. Okay, it does not change the activation energy. The only way to change the activation energy is by adding a catalyst. Okay, I mean, and then in a higher level class, maybe an inhibitor. Okay, anyway, so that is that. And then increasing temperature increases the reactant concentration? No. Okay, it just makes them move faster. Okay, so therefore option C is out as well. And then we have D. So what does D tells us? Okay, tell us. Give me a second. Let me go to my notebook for a fraction of a second. All right, here we go. So if you can remember, in a previous life, we talked about distribution of speeds of a particle at a given temperature. Okay. So if this is my fraction of particles, okay, at a given temperature, let me have the kinetic energy on the y-axis, x-axis. Let me say this is kinetic energy. Okay. At a given temperature, we're going to have a distribution of kinetic energies. Something like that. Okay. So let's say that this is my T1. Okay. And then if I increase, before I increase the temperature, I'm going to do something. Let's say our activation energy of the reaction is this much. This is the activation energy of the reaction. Okay. Now, at temperature T1, the fraction of molecules that has energy greater than the activation energy is about this much. This is the only molecules that can, have effective collisions to become products. Okay. So this is the fraction of molecules that has energy greater than activation energy. But if we have a higher temperature, right? Let me draw this further. If we have a higher temperature than T1, this distribution is going to change to something like this. Right? Now, the fraction of molecules that has an energy greater than the activation energy is this much. You see that increase in temperature increases the number or the fraction of molecules that have energy greater than the activation energy, making the reaction go faster. Okay. And that's another reason why increase in temperature increases the reaction rate, because you're going to have more molecules with enough energy. Yeah. All right. I think that should be enough time for this question. So the first thing you need to do is to balance the chemical reaction. You see sodiums are balanced, oxygen's 1 and 1. Chlorine is an issue. Nitrogen is 1 and 1, hydrogen 3 and 3. So everything else is balanced except for chlorine. We have 1 on the reactant side, but 2 on the product side. So I'm going to split this into 2. So I'm going to multiply this by 1/2, and that will give me 1 chlorine on the product side as well. We are done. This is balanced, right? But it's not the way we present the balanced chemical reaction. Even though this is balanced, we don't want to have fractions, so we multiply everything by 2. So if we do that, we get 2 here, 2 here, 2 here, and this 2 in the denominator will cancel out. That should be your balanced chemical reaction. Do we have any questions, concerns, comments about that? That's it. That's all you had to do there, right? They're asking to produce 100 molecules of chlorine. How many molecules of sodium oxychloride are needed? Okay. To produce 1, we need 2. Oh, we did. Okay, anyway. This is NaOCl. To produce 1, we need 2. To produce 100, we need, 200. That's it. That's your correct answer, option C. All right. What questions, concerns, comments do we have? Okay. So this question is mainly about balancing equation, just like Unit 4, Module 1A homework assignment, not, Unit 4, Module 2 homework assignment. All right. So with that, let me clear my doodling. Oh, okay. Yep, some of us have to stick with A and B. That's okay. All right, let's do this. Oh, this is a nice periodic table. Here we go. This thing, all of these are ionic compounds, okay? So when it comes to ionic compounds, the potential energy, I think we even wrote that, okay? So stronger the ionic force, lower the potential energy, okay? That's the mantra we have been using. And it's kind of obvious as well. Strong ionic force means ions are attracted strongly to each other. Therefore, you're going to have a lower potential energy. Okay, that's the idea. All right. Anyway, so when it comes to these guys, let me see. So the most popular answer was Al2S3 was the lowest. Okay. Then cobalt sulfide. and then lead sulfide. And then the highest potential energy was Na2, sodium sulfide. Okay, this is the highest, and this is the lowest. Okay. Now, why was this the case? All right. I'm going to use a different color. Okay. Aluminum is always +3. Sulfur is always -2. Therefore, the charge product here is 6. Okay. And then cobalt sulfide. Sulfur is always -2. Therefore, cobalt must be +2. Therefore, the charge product is 4. And lead sulfide, sulfur is always -2. Therefore, lead must be, or Pb is plumbers or something like that. Okay. Should be always, not always, should be +2 in this case. Therefore, the charge product is 4. In sodium sulfide, sulfur is -2. Sodium is always +1. Therefore, the charge product is 2. So we know the ionic force is directly proportional to the charge product. We think about the absolute value here when we talk about the charge product, and inversely proportional to the distance between the ions squared. Okay, greater the charge product, that's the primary factor. Greater the charge product, stronger the force. Therefore, Al2S3 must have the strongest ionic force, meaning lowest potential energy, and Na2S must have the weakest ionic force because of the lowest charge product. Therefore, the highest potential energy. Okay, again, the mantra is the stronger the attractive interactions, the lower the potential energy. Okay, and between cobalt sulfide and lead sulfide, now I need to move up a little bit. Okay, so cobalt is over here, and then lead is over here. Okay, so you see that you have 1, 2, 3. So lead has many more shells compared to cobalt, right? As a result of that, lead must be a much larger ion compared to cobalt. Therefore, even though they had the same charged product, okay, lead is a larger cation compared to cobalt. Therefore, the distance between the ions in lead sulfide is greater, meaning you have a weaker ionic interaction in lead sulfide compared to cobalt sulfide based on the size of the ion. Okay, so if we compare this, let me use a different color again. Okay, so cobalt sulfide, let's say that our positive ion is this, and the negative ion is this. And when it comes to lead sulfide, lead positive ion is this much, and the negative ion will be the same size. Okay, you have a greater distance between the ions in lead sulfide compared to the cobalt sulfide, and that's why the interactions are weaker. Because if you have a greater distance between the ions, your interactions are weaker. Because if you want to have strong interactions, you need to be closer to each other. That's the idea there. All right. What questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? All right. So with that, let's do another one. I'm going to clear my doodling. 4, 3, 2, and 1. All right. Let's see what we have. Yeah, most popular answer is B, and that's the correct answer as well, 91%, which is great. Okay, one more time for the sake of other people who did not get this right now. Okay, so the way we do this is we first start with the known. Okay, what is known is the phosphorus, because zinc is a transition metal, and transition metals can have variable charges. Therefore, we are not going to start with that. We're going to start with what we know. All right, so we know the phosphorus has a charge of -3. Why? It is in the 5th group. For it to become a noble gas, it is easy to gain 3 electrons. If it gains 3 electrons, it's going to form -3. But you have 2 of them. 2 times -3 is -6. So the anion side has a charge of -6. Therefore, the cation side should have a charge of +6 for it to be a neutral ionic compound. Because you have 3 cations, this +6 must be divided by 3 to get the charge of 1 cation, and +6 divided by 3 is +2, and that's how we determine +2 as our answer. All right. What questions, concerns, comments do we have at the moment? Anything? Yes, I see a question. Unit 3, module 3. Ionic compounds, yeah. All right. What questions, concerns, comments do we have at the moment? Any other questions? All right. So, all right. I think that should be enough time for discussion. I'm going to close it in 5, 4, 3, 2, and 1. Right. And here are our responses. Yeah, most of us got this as the correct answer as well. And how do we know this is the answer? Aluminum is in group 3. It's going to form +3. That's a fixed cation, fixed charge for that element. And phosphorus is going to form -3. Why? Because it's in group 5. Therefore, to neutralize one aluminum ion, you just need one phosphide ion. Therefore, the correct formula is ALP. Any questions, concerns, comments about that? Anything? All right. So with that, let's move on to a different question. Let's see. All right. So first of all, chromium 2 nitrate. Okay. It should be Cr, and nitrate is -1. Okay. So you're going to need 2 of them to neutralize one chromium ion for chromium 2, because chromium 2 means chromium 2 plus. For chromium 4 nitrate, chromium is 4 plus charge. Therefore, to neutralize one chromium 4 plus ion, you're going to need 4 nitrate ions. So therefore, this should be the formula of chromium 4 nitrate. It's just, writing the whiteboard question for you. Okay. Now, which one should have a lower melting temperature or higher melting temperature? Okay. So for chromium, let me use a different color. For chromium 2 nitrate, chromium is +2 because you are told that it is the case, and nitrate is -1. The charged product is 2. And for chromium 4 nitrate, chromium is +4, and nitrate is always -1. The charged product is 4. Because you have a greater charged product in chromium 4 nitrate, the melting point must be greater for chromium 4 nitrate compared to chromium 2 nitrate. That's number 1. Okay. And that should be, let me see your options, your answers. Okay. Here are your responses. That should be option B. Chromium 2 nitrate has a lower melting temperature. And then chromium 2 nitrate has smaller charges. Yep, that's the main reason, because you have smaller charges in chromium 2 nitrate, and that's why the charged product is lower there, and that's why the ionic force is lower, making it have a lower melting temperature. That is correct as well. And then chromium 2 nitrate has smaller ions, and large ions. So it's almost like 50-50. Okay, one of them has small ions. Now, anyway, so here's how we do it. Chromium 4 plus and chromium 2 plus have the same number of protons. Okay, but chromium 4 plus has less electrons. Okay, because chromium 4 plus has a greater positive charge, those electrons of chromium 4 plus will be more strongly attracted to its nucleus, making it a smaller electron cloud. Therefore, chromium 4 plus, let me write it out, chromium 4 plus is a smaller ion compared to chromium 2 plus. Why? Because you have a greater charge. I'm referring to this charge over here. Okay. These electrons are more strongly attracted to this chromium nucleus. They're making it a smaller electron cloud. Okay. That's why chromium 4 plus chromium 4 nitrate has small ions, and chromium 2 nitrate has large ions. So the correct answer is, let me point it out, should be this. All right. What questions, concerns, comments do we have at the moment? Anything? Any questions, concerns, comments? All right. So, now, which is great. All right. So really quickly, before I look at your answers, okay. So element X has one valence electron for it to become like a normal gas, it is easier to remove one electron minus, okay, one electron. If it removes one electron or one negative charge, it's going to form X plus ion, X plus 1 ion. On the other hand, Y has 5 valence electrons. For it to become like a normal gas, it is easier to gain 3 electrons. Okay. So you're gaining 3 electrons. If it gains 3 negative charges, it's going to form Y3 minus ions. Therefore, to neutralize one Y3 minus ion, you're going to need 3 X plus ions. Therefore, the chemical formula is X3Y. What questions, concerns, comments do we have about that? Anything? Any questions, concerns, comments? All right, I'm going to move on to worksheet 16. Is it A, Carter? Okay, 16A. Let's see if I can do it. By the way, I'll open the attendance code as well. I'll leave it open. 6803. And then 16A. First one, first question. Yeah, let's do the first question of 16A. Moles to mass A. Go ahead. And these questions are related to the last part of day 1 of unit 4 module 1, where we talked about stoichiometric calculations. And also the second video I posted, which I named as Thanksgiving Special, I went over all the unit 4 module 2 questions. Well, not all of them, 70% of them. And that covers questions like this. All right, first thing is to balance the chemical reaction. Make sure that you do that. Yeah, 4 phosphorus atoms on the reactant side. So we need to multiply pH3 by 4. That will give me 12 hydrogens on the product side. Therefore, I need to multiply this by 6. This should be the balanced chemical reaction. What's the element? Phosphorus. I don't know if you're table handling that. You want. Right, and you might need the molar mass of pH3 over here, which you can determine by the relative atomic masses of phosphorus and hydrogen. Phosphorus is 31. And then hydrogen is 1. You have 3 of them. Altogether, it should be 34. You got it? 34 grams per mole. All right, I'll try to do this on okay, anyway, over here, actually, on the screen itself. Maybe not. Yeah, it's easier to do this way. I'll do this here. All right, so this is what we have. Now we are given the mass of pH3, 100 grams of pH3, but they are asking for the moles of hydrogen. Okay. Oh, they're asking for the moles of hydrogen in the question. Okay, so we need to go from mass of pH3 to moles of hydrogen. So let's do this. Okay, first of all, I want to cancel out the grams of pH3. So if I divide this by the molar mass of pH3, because 34 grams of pH3 is the mass of 1 mole of pH3. Okay, I can cancel out the grams of pH3. Now I'm in the moles phase, but it's pH3 moles. I want to convert this to moles of hydrogen. To do that, I go to the balanced chemical reaction. Okay, I see to get 4, this is 4, right? Yeah. To get 4 pH3, I need 6 hydrogens. Therefore, I'm going to write 4 moles of pH3 here from the balanced chemical equation. And then 6 moles of hydrogen over here. 6 moles of hydrogen over here. So moles of pH3 cancel out. If you plug and chuck these numbers, you should get the moles of hydrogen because that is what is left. So what you need to do is, in the numerator, we have 100, and then we have 1, and we have 6. And in the denominator, we have 34, and then we have 4. And this should give me the moles of hydrogen as your answer. This is it. You need to do the calculation. Okay, so this is multiplication, by the way. Can you give me the answer? And the answer is 4.4 moles of hydrogen. That should be the answer. Can you check that too? Yeah, perfect. All right, so I think that's it. So do your best preparing for the exam. I told you, how to do it. 1-page note and the 2 review exams, and then go over the homework and the past quiz questions. That's it. Don't do anything else. And during the exam, have fun. Just relax and have fun after doing your best to prepare. Bye, everybody. See you Friday. Something again? Yeah. I'll let me prepare the room for the other one. Mm-hmm. Hi, Dahlia. What's up?